Number of functions from number of functions from a non-empty set A to a non-empty set So we are starting with this topic. How to find number of functions from a set A to a set. Here that is the function is set F mapping from A to B. Now all of us know that when there is a function from A to B, is a set A is there, set B is there, both are non-empty set. And whenever we have functions from A to B, that means what? When a function A is defined from a non-empty set A to a non-empty set B, all the elements in the set A should have distinct image in set B. So we know that when we have a function A defined from a non-empty set A to non-empty set B, all the elements in the set A should have a distinct image in set B. That is the definition for a function to exist from A to B. Now here I consider that cardinal number, since it is a non-empty set, it's a finite set. So we consider cardinal number of A as n and cardinal number of B as r. Now we take a set. Here set A, here set B. I consider here n elements x1, x2, x3, xn, y1, y2, y3, yr. Now, when it is a function, what we should have, all the elements here should have distinct image. Now, first of all, one thing you have to keep in mind that the correspondence which you are taking, that should be either many one or one. It should not be one to many correspondence. So, for first element, how many options we have? When the function A is mapping from A to B. Now, element x1 can be mapped to elements of B in how many ways that we're trying to find. So first of all, element x1. For the element x1, we have how many choices there in the set B? R choices. Right. For the element x1, there are R choices in set B. Similarly, for the element x2 also, there are R choices. In set B. Now, here you have to understand one. As I have given an example earlier for the function, but for understanding function, you can consider that here we have a set of students in a class, and here is their birthdays. Now, one student can have one birthday, two students can have the same birthday, but one student should not have two birthdays. Now, here what you have told, x1 have R choices. That is, it can be mapped to anyone you like. X2 also have R choices. Why? Suppose X1 is mapped to Y1. Now X2 can also be mapped to Y1. Two students can have the same birthday. So X2 can also be mapped to the same element, no issues. So here also we have R choices. So like this, if we go on for the element Xn also, for the element Xn also, there are R choices. There are R choices in set B. Is when we have X1 have R choices, X2 also have R choices, Xn also have R choices. Now, here what is the main thing here, that all the elements, not a single element or two element or five elements, all the elements in the set A should be mapped to the elements of the set B. So here, how many choices are choices? Here, how many choices are choices? For Xn also R choices. Now, all the elements in the set A should be mapped to the elements of set B. Okay, so that means all this operation should be done. Now, when all this operation should be done, that means what? By fundamental principle of counting, you have addition principle, multiplication principle. Here is multiplication principle should be applied. Why? Because the whole system of work will be done when each of this set of operations is done. So here, write it down. By fundamental principle of counting, by fundamental principle of counting, in bracket, total number of ways, total number of ways equal. Now here, let us write it properly. Multiplication. Now, number of ways will be what? R into R into R, like this. R only. And now, how many R we have multiplied? For n elements you have taken into consideration. Here you had n elements. So here what we'll do? How many times you have taken? N times. So what is the answer here? R to the power of n. In another way, you can think this one, that number of elements in codomain to the power number of elements in domain A 1, 2, 3 and set B 1, 2. Now here the function is coming from what? From A2. So which is the codomain? Codomain is a set B. Here codomain is a set B. Now, as we have done just now, that is in this case, number of functions is what? Write down number of functions that can be defined from set A to set B equal to what I told, number of elements in the codomain to the power number of elements in the domain. So number of elements in the codomain, how many we have? We have 2 elements, and number of elements in the domain 3. So it is 8 elements. 8 functions are possible. Number 2, number of functions from A to A. F maps A to A. So here, how many functions are there? Write down number of functions from A to A, from the set A to set B. Now, when we have number of functions from the set A to A, what is the, as per the formula? Here, what is the codomain? Codomain is A. What is the domain? Domain is A. So, what we can write here? N to the power of N. This is the same thing. Here, number element in the codomain is what? N. Number element in the domain is what? N. So, it is N to the power of N. Now, according to condition, what we can say? N to the power of N equal to 256, which we can write as 4 to the power of 4. Therefore, what is N? N is 4. Number of 1 function. Now, what is number of 1 function? Here in this topic, number of 1 function, what we're going to find? How many functions are possible which are injective from the set A to set B? From the set A to set B. Now, as you know, what is an injective function? That is, here we take a set A, here we take set B. Set A to set B. Now here we have assumed that cardinal number of the set A is N, cardinal number of the set B is R. Now this is then x1, x2, x3, xn. This is y1, y2, y3, yn. Now you know here, when it is a 1 function, when f is mapping from A to B, is a 1 function. When we have f maps A to B is a 1 function, that means what? All the elements in the domain should have distinct image here, and simultaneously all the images here have distinct pre-image. That means what? Suppose we say, we take a different example. We take a small set A having 3 elements, and here I take a set B which is having 4 elements: A1, B1, C1, D1. Now suppose 1 is mapping to A1, 2 is mapping to C1, and 3 is mapping to D1. So this is a 1 function. Here what happens? All the elements in the first set have distinct image in the second set. Similarly, all the elements in the second set have distinct pre-image. Here all the elements in the second set have distinct pre-image. So in this case, when we say a 1 function, definition all of you know, that is when f maps from A to B is 1 function or injective function, then if x1 not equals to x2, this implies if x1 not equals to x2. Now that is the formal definition. So here f map from A to B is 1. Now that is a very important criteria. With that, there is another important criteria. Here if you see, here there is 1 to 3 element. I have taken A1, B1, C1, D1. Similarly, I could have taken in this way. Suppose this is one case. There is suppose another case. This is set A, this is set B. Now here I take 1, 2, 3. Here I take A1, B1, C1. Then also it is possible to have 1 function. Here you can see we can have a 1 function. Here f is mapping from what? From A to B, and here is 1. Now there can be another case. Suppose you set A and you set B. Here we have x1, x2, x3, suppose 3 elements. But here I have only 2 elements. Now here, no question of 1 function, because under any situation, if you see the least case also, suppose here 1 element is mapping to A1. Next, suppose x2 is mapping to B. Then x3 have either two choices, either A or B. Suppose I take 2B, then also it is many one. If I take it to A, then also it is many one. That means one function will be possible only when number of elements in the codomain is greater than equal to number of elements in the domain. Number of elements in the codomain greater than equal to number of elements in the domain. So this is one criteria, that all the elements in the domain should have distinct image in the codomain, and all the that is here, whatever the elements we have, these are the pre-images, these are the images. That is, they are having distinct images. Similarly, images have distinct pre-image. All of you know, these are what? These are called pre-images. These are called what? These are called pre-images. And these are called what? Images. These are what? Images. Now, as all the pre-images have distinct image, all the images should have distinct pre-image. Now, there is one criteria. So, this is a one possible, this is a one possible, but here one not possible. So, from this, what we conclude? Right, for one function to exist, for one function to exist, number of elements in codomain that is R should be greater than equal to number of elements in domain. That is same. So this is a very, very important criteria. The number of elements in the codomain should be greater than equal to number of elements in the domain. Now, with this you mention. Now, when R less than n, then number of one function is 0. Then number of one function is equal to 0. Therefore, one function to exist, number of elements in the codomain should be greater than equal to number of elements in the domain. And this condition you will keep in mind: when R less than n, number of one function is 0. With this, what I told you, that whenever it is a one function, all the elements in that domain should have distinct image, and images should have distinct pre-image. Now, with these two concepts, we'll find the number of one function. At first, we think it in this way, that when we are mapping from 1 to n, elements from 1 to n, x1 has how many options? R options. x2 has how many options? Then R minus 1 option. Why? Suppose x1 is mapped to y1. Now x2 cannot be mapped to y1. So write it down. For number of one function. For number of one functions. Element x1 have R choices. Element x1 have R choices. Element x2 have R minus 1 choices. Why? Because suppose x1 has been mapped to y1. x2 cannot be mapped to y1. So now for x2, we have R minus 1 options. Element x2 is mapped to suppose any other element y3. Now for x3, we will have R minus 2 options, because x3 cannot be mapped to y1 or y3. So here, element x2 have how many options? R minus 1 options. Now element x3 have R minus 2 choices, and so on. Now, element x1 have R choices. So this one we can write in another way to understand that when x1 will have how many choices? x1 have r choice, so that I can write r minus 1 plus 1 choices. Now for the next one, r minus 1. So what we can write? R minus 2 plus 1 choices. Next one, R minus 3 plus 1 choices. Just if you observe, for x1, R minus 1 plus 1. For x2, R minus 2 plus 1. For x3, R minus 3 plus 1. So when we go like this to element xn have R minus n plus 1 choices. R minus n plus 1 choices. Now the whole mapping will be completed when? When all these operations are done. Whole mapping will be completed when? When all the operations are done. Write it down. Mapping will be completed. Mapping of elements in domain set in domain will be completed when all the elements are mapped under considered restriction. So since the whole system will become whole work will be done when each of the operations is completed. Therefore, here what we will apply fundamental principle of counting multiplication. So this will be equal to what? R into R minus 1 into R minus 2 into R minus n plus 1. Now this we multiply with few more numbers. These are some extra numbers which we should multiply. So we'll adjust. There is R minus n into 3 to 1 or 1 to 1. So this gives us what? From 1 we have taken R elements. So this will be what? R factorial 5. Here from 1 to R minus n. So here what we write? R minus n factorial. That is RPN. Number of 1-1 function from the set A to set B. Set A is having elements 1, 2, 3. Set B is having elements A, E, I, O, U. So here NA is what? NA is equal to 3. NB is what? NB equal to 5. So first thing is here NB is greater than NA. So definitely 1-1 function possible. Therefore, number of 1-1 functions equals to what? RPN. What is R? R is this one. What is N? Number of element domain we take as N. And number of element in the codomain we take as R. So this will be what? This will be 5B3. Next we come to fourth question. Number of 1-1 functions that can be mapped from the set A to B. Here number of 1-1 functions that can be mapped from the set A to set B. What is given? A as 4, 8, 12, 16. And B, nothing is given. So we take as R. So now we write number of 1-1 function equal to RP4. Why P4? Because here NA is equal to 4. Okay. And that is equal to what? 5040 given. That is equal to what? 5040. Now, if you simplify this, what we get? R factorial by R minus 4 factorial equal to 5040. Now, this can be simplified further as R into R minus 1 into R minus 2 into R minus 3 equal to 10 into 9 into 8 into 7. And therefore, we conclude that R is equal to 10. That is, in B equals to 10. Function A from A to B. Here, NA equal to 7. NB equals 10. Number of one-on functions. So, here what we understand. NA in B is or NA is less than N. Therefore, number of one function equal to NB PNA. That is RPN. So 10P7. Number of many one function. Now see how we find number of many one function. Now when a function, there is a function A mapping from A to B children. Whenever there is a function A mapping from A to B, if this function is either one function, is either a one function or many one function or many one function. Either a one function or a many one function. That is total number of functions. That is total number of functions is equal to number of one function plus number of many one function. Number of many one functions. So if we want to find number of many one function, how do you find that? Total number of function minus number of one function. So therefore, number of many one function, number of many one functions is equal to total number of functions minus number of one functions. Total number of functions minus one function. So here, what we do? Total number of functions we already know. Total number of functions is what? R to the power of n. Number of elements in the core domain to the power of number of elements in the domain. So here we can simply put the formula R to the power of n minus. Now minus what? R to the power of n minus RPN if R is greater than or equal to n. And this will be R to the power of n if R is less than n. So when R is less than n, there is no question of one function. So we have only many one function. So R to the power of n minus RPN if R is greater than or equal to n, and R to the power of n if R is less than n. Total number of possible many to one functions. Now set A is having here 6, 36. and set B is having 1, 2, 3, 4, 5. Now here what is N? N is 2, which is our N. What is NB? NB is 5, which is R. Okay. Now here, at first what we'll do? At first we find total number of functions. Total number of functions. That is what? R to the power of 5 to the power of 25. Then I find number of 1 function. Number of 1 functions. RPN. That is 5P2. That is what we have. 5P2. 5P2 means 5 factorial by 3 factorial. So that is what 20. Therefore, number of many one function. Number of many one functions equal to 25 minus 25. Number of onto functions. So here we will understand first number of into function, number of onto functions. So with that actually, here we are going to study mainly first number of into function. We'll discuss both of them. What is the onto function? All of you know, suppose if it is F mapping from A to B, we take here the cardinal number of A as N, cardinal number of B as R. Now this set A, this set B. I have taken here N elements like this. Here Y1, Y2, Y3, Yn. Now when it is set to be on, when all the elements in the codomain have pre-images, or pre-images, that is basically, in short, when codomain is equal to range. That is, all the elements in the codomain have pre-image. When all the elements in the codomain have pre-image, then what is say? Function is on. So write it down. F maps A to B is said to be onto when all the elements in codomain have pre-image. Then what we say is on. If it is not so, if there is at least one element in the set B which has no pre-image, then it is into function. If with that you write it down, F maps A to B is said to be into function when there is at least one element in codomain, that is set B, which has no pre-image. That is, if there is any element here which has no pre-image, then it will be at least one element. It can be more than that also. As no pre-image, then what we say is into function. When we have function mapping from A to B, when we have functions mapping from A to, functions will be either into or on, either into or on. So if we can find number of into functions, then we can find number of on functions also. So at first we try to find the number of into functions. Number of into functions. How will we find number of into functions? We take few sets that let B1, B2, B3, Bn be the cases, or be the set containing the cases also you can think, or cases, be the cases where y1, y2, y3 dot yr does not have preimage, does not have preimage. So what we are saying that these are the cases when y1, y2, y3, yr doesn't have any preimage. Now in this case, when try to understand, when y1 is not having preimage, it can be in many ways. How many ways? See, suppose I take here two sets. Here I take two sets, set A and set x1, x2, x3. Here you have y1, y2, y3. Now I'm saying that y1 doesn't have preimage. It can be many ways. It can be that all the elements have been mapped to y3. It can happen. This is a case possible. Now it can be like this also. Set A, set B. Here x1, x2, x3, y1, y2, y3. Now here it can be that x1 is mapped to y2 because we will not, that y1 will not have any preimage. It can be like this also, and all the other elements mapping to y3. It can happen. There can be other cases also, like this also another case I take. Is set A, is set B. Is x1, x2, x3, y1, y2, y3. Now, if it is like that, and all the elements are mapped to y2, that can also happen. So there are various ways out there where it can happen that y1 doesn't have any preimage. V1 will contain all those cases where y1 will not have preimage. Similarly, y2 will not have preimage, y3 will not have preimage, yr will not have preimage. So here I mentioned set of cases. Why set of cases? Because here all those cases have been contained in V1. V1 is what? A set of cases when y1 doesn't have preimage, y2 doesn't have image for b2. b2 is a set of cases where y2 doesn't have preimage. Like that, we have taken bn. Here it is br, not a. So br is a set of cases where yr doesn't have any preimage. Now, what is our intention? Our intention is to get this now. N of B1 union B2 union B3 union BR. What is this? Union means what? This is 2, 3, collect. Children, those three case set. I just take those cases where we had three sets. I take here three sets like this. Now, when we say union, of A, B, C, what is the meaning? That is, the element is either in A, either A condition is satisfied. Here the element, or this element, or this, or both, or three of them. This is what we know. N of A union B union C. What is that? NA plus NB plus NC minus n of A intersection B minus n of A intersection C minus n of B intersection C plus n of A intersection B intersection C. So any one condition, if at least one of the element, at least one of this element doesn't have P image, it is into. When it is into, function be into when. For function to be into, at least one of the elements should not have P image. So if you find this one, then you are done. Because this means what? At least one of the cases occurring here. So when we are finding number of into function, if we find this, then we are done. This means what? Either this or this or this or both. So all the cases are involved here. So if we find this, then we are done. Now, this means what? This means what? If we find this, what will be the meaning of this? This is a summation of NB1. Yeah, like at first we have added. This is called what? This is called inclusion. You are adding inclusive. And here you are separating exclusion. When you are separating this one, these together, what they call exclusion. Again, when you are adding, you are including. So this is inclusion. So inclusion, exclusion, inclusion. These are inclusion, exclusion principle, you can see. So here what I say, summation of NB1. Like this, I have added. Next it will be what? Minus summation of N of B1 intersection B2. There is inclusion, exclusion. Now again inclusion. Plus summation of N of B1 intersection B2 intersection B3. Again exclusion. So this will continue like this. So this will be the number of into function. This is what? Number of into functions. Now how to find this on NB1? NB1. That means what? Here one element y1. Not only y1, it's NB1 means only y1 case. Number of is for y1. Okay, number of is for y1. But when it is summation of NB1, then it is NB1 plus NB2 plus NB3 like that, NBR after. So when I write only NB1, that means only the number of cases where y1 doesn't have pre. Y1 doesn't have any preimage. Now, in this set, suppose I say y1 will not have preimage, so I block this. Now, for each of the element, how many options are there? X1 will have r minus 1 option. X2 will have r minus 1 option. X3 will have r minus 1 option. Xn will have r minus 1 option. So when they are not mapping to y1, then for each of the element, how many options? R minus 1 option. When y1 does not have preimage, then for each element in domain, there are r minus 1 choices. There are how many choices? R minus 1 choices. Therefore, number of cases will be r minus 1 to the power of n. Because for each element r minus 1, so how many elements we have? N elements. So r minus 1 to r minus 1 to r minus 1, r minus 1 to the power of n. So this is for NB1, r minus n to the power of n, r minus 1 to the power of n. For each element we have r minus 1 case, so r minus 1 to the power of n. Now, when I write summation of NB1, then what we have? Summation of NB1 means all we are adding. Now, that means what? This can be anyone. Summation of NB1 means when you find summation of NB1, basically what you are finding? You are finding anyone you are taking here, RC1 suppose. can be y1. For y1 you can find, for y2 you can find, for y3 you can find. So RC1 into, when anyone you are taking, into what? R minus 1 to the power of n. Suppose RC1 means what? Anyone you have taken. RC1 means what? Anyone you have taken. Suppose y1, R minus 1 to the power of n. For y2, R minus 1 to the power of n. So RC1 means what? R cases y. The summation of NB1 means what? B1 plus B2, NB1 plus NB2 plus NB3 plus NBR. That is the reason it is actually R into this one. So that I have written as RC1 into R minus 1 to the power of n. Number of choices such that one element doesn't have p-units. This one actually representing what? Number of choices one element doesn't have p-units. Next, what we have to find to see here, n of p1 intersection p2. That's now two elements will not have p-units. Now, when we find summation of n b1 intersection b2, there is now two element is not having pre-image. So what we'll do? RC2 now we'll choose any two element which will not have pre-image. Now in that case, what I'll do? Suppose I choose y1 and y3 will not have pre-image. So now for each element we have how many options? R minus 2 option. For each element now how many options? R minus 2 option. So now we can write here R minus 2 to the power of n. This is what? Is the number of choices. Number of choices such that two elements does not have pre-image. Two element doesn't have pre-image or pre-image. Similarly, we have to consider the other case also. In B1 intersection B2 intersection B3 summation. So here what we have RC3. Number of choices such that three element doesn't have pre-image in R minus 3 to the power of n. Because now what we are doing, now we are dropping suppose another element. So now for each element, how many options? R minus 3 options. So that is what? R minus 3 to the power of n. Now, what is our intention to take? N of B1 union B2 union B3. That is what? Summation of n B1 minus summation of n B1 intersection B2. There is inclusion, exclusion, plus summation of n B1 intersection B2 intersection B3. Again inclusion like that. So this is what RC1 R minus 1 to the power of n minus RC2 R minus 2 to the power of n plus RC3 R minus 3 to the power of n. Like this will continue. So this is what? Number of into function. This is what? Number of into function. Number of into functions. When you go to number of onto function, before that, you have to understand the very important thing. Suppose we have a set here, A, and a set B. Here we have x1, x2, xn element. Here we have y1, y2, yr. Now, is always onto function possible? Is there always chance of onto function? Why don't we see? I have taken here three element 1, 2, 3. And here I take set B having 4 elements. No chance of on function. Why? Suppose this is the case. If each element, if there is one function also existing, then also there will be at least one element which will not. Here if it is one, then one element which will not have the image. Suppose if it is many one, suppose the same case is I take set A and here I take set B. It is 1, 2, 3. Here A1, B1, C1, D1. If it's a many to one correspondence, then there will be more than one element which will not have the image. So that means what? When it is an onto function, when it is onto function, not into onto function, then it is mandatory that then when it is onto function, it is mandatory that R is here this element, there's a number of elements, this co-dimension R is less than equal to N. Or in other way, N is greater than equal to R. Now, that is, we are getting onto function when number of elements in the domain is greater than equal to number of elements in the co-domain. Otherwise, you can say we will not get onto function. So write it down. F mapping from A to B. F mapping from A to B. Onto function exists if N greater than equal to R, either greater than or equal to. If it is not, then no onto function. Onto function. Number of onto functions will be what? Number of functions minus number of into functions minus number of into functions. Number of into functions. From the total number of function, if we subtract the number of into function, then we get number of onto function. The number of functions already we know R to the power of n minus RC1 R minus 1 to the power of n minus RC2 R minus 2 to the power of n minus plus here, inclusion, exclusion, inclusion plus RC3 R minus 3 whole to the power of n. Now this gives us what? R to the power of n minus RC1 R minus 1 to the power of n plus RC2 R minus 2 to the power of n minus RC3 R minus 3 to the power of n. Continues. So this is the formula for number of onto functions. We take question number 8, where it is given that set A is having elements 1, 8, 11, 14, and 25. That is, it is a finite set with cardinal number 5. Now, here we have to define all the functions from A to B, which will be surjective function. Now, for that, we have to find the condition that what is the cardinal number of B for which this will exist. What can be the cardinal number of B for which it can exist? So, we can say that if will be a surjective function, f will be a surjective function when cardinal number of B is less than or equal to cardinal number of A. Cardinal number of A is 5. Therefore, what we can say that NB should be less than equal to 5. Therefore, NB should be less than or equal to 5. Now, next we take question number 9. Question number 9 is quite similar to this concept which you have done just now. Here it is given that set A has a cardinal number 4, obviously finite set with cardinal number 4. NB is also a finite set quadrant number 6. That is what we understand here. That is NB is greater than NA. NB is greater than NA. Since NB is greater than NA, so no surjection is possible. So we can say number of surjection possible from A to B is equal to 0. So very simple concept. Since here what we understand that cardinal number of B is greater than cardinal number of A, so number of surjection function should be 0. Set A 4, 5, 6, 7, 8. Set B 1, 2, 3. Now here what we see, ANA, that is number of elements in the domain, is greater than number of elements in the codomain. So definitely suggestion number of the suggestion function is possible here. So write number of surjection. Number of surjections from set A to set B. Now here, as per the general formula, R to the power of n minus RC1, R minus 1 to the power of n plus RC2, R minus 2 to the power of n minus RC3, R minus 3 to the power of n. I take here up to 3 only because here the R is 3. R is what? R here is number of elements in the codomain, that is 3 here. And n is number of elements in the domain, which is 5 here. So now we'll substitute the values to get the result. 3 to the power of 5 minus 3C1, 3 minus 1 to the power of 5 plus 3C2, 3 minus 2 to the power of 5. Next one, no need to write because 3 minus 3 to 0. So this is the number of surjection. So this is what we get as a number of surjection. If we calculate what we get, 150. Set A is having 1, 4, 9, 16. Number of so not surjection, or you can think this one as number of into function. B 2, 8, 16, 32, 64. Now here what is NA? NA is equal to 4. What is NB? NB equal to 5. Therefore, NB greater than NA. So no surjection exists from set A to set B. So therefore, number of non-surjection equal to what? Number of functions. Because basically, if you subtract number of onto is 0, number of onto or surjection is 0. So number of functions only. So what is the number of functions here? Number of elements in the codomain to the power number of elements in the domain. So that is 625. What we have, set A is having 1, 2, 3 up to n. Set B is having 2 element A, B. Now here they ask for what? Number of surjection. Now try to understand this. This is set A, which is having 1, 2 up to n. set B, we have here two elements. Now, when we see the number of functions only, what is the number of functions here? Number of elements in the codomain to the power number of elements in the domain. Why? Because here you can understand each element have two options. Either it will be mapped to A or mapped to B. Two also mapped to A or mapped to B. So for all the elements, we have two options. Either mapped to A or mapped to B. Now out of these, there are only two into functions. When all the elements are mapped to A or all the elements are mapped to B. Now, if we remove that two into function from the whole number of functions, then we get number of one function. So, write it down. Here, for each element in domain, set A, there are two choices. Either A or B. Either A or B. Therefore, number of functions two to the power of A. Number of functions 2 to the power of A. Now, out of these, there are only two into functions. Why? When all the elements are mapped to A or all the elements are mapped to B. Write it down. Out of which there are two into functions. There are two into functions. When all the elements are mapped to element A or mapped to element B. Okay, there are only how many functions? Two into functions. When all the elements are mapped to A or all the elements are mapped to B. Therefore, number of onto functions equal to 2 to the power of n minus 2. Number of bijective function from a non-empty set A to a non-empty set B. Now, first of all, you have to understand if mapping from A to B is said to be bijective when function when f maps A to B is 1 function and f onto function, or you can say surjective function. Both has to be satisfied. Now, 1 function, suppose the set A is there with cardinal number n, set B with cardinal number r, set A with cardinal number n, set B with cardinal number r. Here x1, x2, x3, xn. Here y1, y2, y3, yr. Here we have n element, here we have r. Now, when this when this is a number of 1 function possible, we have a restriction on n and r. What is the restriction? That it is possible to have 1 function when r is greater than equal to n. We can have 1 function when r is greater than equal to n. So write it down. For 1 function to exist, r greater than or equal to n. And for on function to exist, r less than equal to n, which we have done just now. R less than equal to n. Now for bijection, both is to be satisfied. For bijection for function f mapping from a to b to be bijective, both the conditions are satisfied. Now both will be satisfied when r equals to, for function to be bijective, both has to be satisfied, both the conditions to be fulfilled when r is equals to n. Now here we have set A and set. Both have cardinal number n. Both have cardinal number n. And it should be 1, 1 as well as 1. So how is that possible? As you can think here, the different balls we have, and we have different boxes. Each box can hold 1 ball only. So for each ball, how many options we have? A for the first ball. We have how many options? N option for second ball, n minus 1 option for third ball, n minus 2 option. So write it down. For element x1, there are n choices. For element x2, there are n minus 1 choices, and so on. So like this, if we continue, for xn, we have 1 choice. For element xn, there is 1 choice. There is how many choices? 1 choice only. Now here, all the operations have to be done, have to be complete to complete the mapping. That is, when the whole work will be complete, when all the operations are done. So by fundamental principle of counting, here we are using fundamental principle of counting. By fundamental principle of counting, multiplication, number of bijective functions, equal to what? Equal to n into n minus 1 into n minus 2, 2, 1. That is what? N factorial. What is given? Cardinal number of A equal to 106. Here, function is mapping from A to A. If the function is mapping from A to A, the number of bijection number of bijection, which you have already seen in the theory. So number of bijections from A to A will be given by NA factorial, which we have discussed already. So here just we use that result and we get here 106 factorial. Very simple. Next we come to question number 14. Here is given function is mapping from A to A. Now cardinal number of A is equal to 3. Now here we have to find number of non-bijective function. So number of non-bijective function is equal to number of functions minus number of bijective function. Okay. Now we know what is the number of functions formula. Number of elements in the codomain to the power, number of elements in the domain, which you have already derived also. So this will be 3 to the power of 3 minus number of bijective function on A. So it is NA factorial. So it is 3 factorial, which is basically 27 minus 6, and that is 21. So here we get number of non-bijective functions, that is which are not bijective, is 21. Number of bijections. Number of bijections with de-arrangement condition. With de-arrangement condition. Now, what is this de-arrangement condition which you have to apply here? Let us take one example. Let F maps A to B. A to A. If it is A to B, then the cardinal number of B and cardinal number of A has to be same. So F maps A to A, and cardinal number of A equal to N. And suppose the set A is having the elements 1, 2, 3 up to N. Now suppose they are saying that we have to find the number of bijection from A to A such that number of bijection we have to find such that, or you can redefine it in this way, that F maps A to A is a bijective function which is required such that F of I not equal to 1. That is, F of 1 should not be 1, F of 2 should not be 2, F of 3 should not be 3, F of n should not be n. That is, if you are taking an element here, the input and the output should not be same. Here there are n cases, and with this we have found the formula for Dn. What is the formula? Dn equal to n factorial 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, like this, up to minus 1 to the power of n into 1 by n factorial. So this will be the number of bijection under this de-arrangement condition. In question number 15, set A is having 4 elements, 1, 2, 3, 4. And F is mapping from A to A such that F of x not equal to x. F of x not equal to x. So here number of bijections under the given restriction will be what? D4, that is 4 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. Calculate, I think I am getting number of strictly increasing function. Number of strictly increasing functions. Now, at first, we will discuss a bit about the strictly increasing function. That is, what is a strictly increasing function? See, yx origin is y prime is x prime. Suppose this one I'm taking. Now it is a strictly increasing function. What's strictly increasing function? Here, if we take any 2 points, suppose xk and xk plus 1, corresponding what we do? Y suffix k and y suffix k plus 1. Now here, I have taken the element such a way that xk plus 1 greater than x, and we take a for xk plus 1 greater than f of x. So this is the condition for strictly increasing function. And if you observe another very important thing, strictly increasing functions are always one function. Strictly increasing function are one function. So write it down. No. Strictly increasing functions are one function. Are one functions. Now suppose we have here two sets. Set A, set B. Here we have element x1, x2, x3, x. Here y1, y2, y3. Now here, since it is one function, when it is possible? If it is a strictly increasing function, what? One function. So one thing is for sure that R has to be greater than equal to n. So strictly increasing functions will be possible when, or will exist when R greater than equal to n. So here we can say strictly increasing functions exist when, under this condition, R greater than equal to n. Okay. Now we have to find here how many strictly increasing functions are possible. Now before we start that number of strictly increasing functions, what we do? At first, you know here as the x values of x increases, values of y should increase. As the values of x will increase, values of y should increase. So at first, what I do, I arrange here the element. I arrange all the elements in the set A in ascending. In a set B also, I arrange them in the ascending order. At first, what I am doing, I am arranging all the elements here in the ascending order, and all the elements in the set B also in ascending order. Now, since you know that here all the elements, distinct elements are. So if we have distinct elements, we can arrange them in how many ways? In one way only. We can arrange them in how many ways? In one way only. Now after that, from these arranged letters, arranged elements, I can choose any for here to be mapped. Done. So that will be the number of strictly increasing function. first. We arrange all the elements in the set A and in the set B in ascending order. As distinct elements are presenting the set A and B in a set A and set B, so they can be arranged only in one way. Because it's a distinct element. Distinct elements can be arranged only in one way. All the elements in set A and set B is order. That is x1 less than x2 less than x3 less than x, and y1 less than y2 less than y3 less than yn. So here all the elements are ordered. So now if all the elements are ordered in a set B, if I suppose choose any element, I take up the different set and I try to make you understand all of you. Suppose here in a set A, I have taken ordered element 1, 2, 3. They're ordered. There is an assembly. And here I have A1, A2, A3, A4, A5. And I choose here any 3 elements. Now they can be mapped only in one. After I choose them, they can be mapped only in one. Listen. After I select them, they can be mapped in how many? Only in one. So here also, once the elements are ordered in one way each, now we can select it down. Now we select n elements out of r elements from the set B in RCNOS, which can be mapped from A to B in one. Therefore, number of strictly increasing function is 1 into 1 into RCN into 1 equal to RCN. First one, the way the elements of the set A has been arranged. This one, the number of ways the elements of the set B is arranged. RC1, number of ways the selection has been made. N elements out of R. Now this one, number of ways it has been mapped. Done. Set A have 1, 2, 3, 4, 5. Set B, we are having -2, -1, 0. 1, 2, 3, 4, 5. F maps from A to B. We want what number of strictly increasing functions. So first of all, NA, how many elements? 5 elements. N, we denote by N. NB, we have how many elements? 3, 6, 8. That we denote by R. So here R is greater than N. Therefore, number of strictly increasing functions equal to RCN, that is 8C5. Yeah. Number of strictly decreasing function. Now, what is the meaning of the strictly decreasing function? We take here one example. Here we have xk and we have here xk plus 1. We have here corresponding yk and yk plus 1. We observe here when xk plus 1 greater than xk, f of xk plus 1 less than f of xk. Now, strictly decreasing functions are 1-1 functions. Strictly decreasing functions are 1-1 functions. You can see. So, if it is a strictly decreasing functions or 1-1 functions, so for strictly decreasing functions, R should be greater than equal to R should be greater than equal to, otherwise it cannot be a 1-1 function. So here we consider this condition because R is greater than equal to N for strictly decreasing function, because all strictly decreasing functions are what? 1-1 function. Now what we see? At first, we arrange the elements of the set A in ascending order. We arrange them in the ascending order. That is as the, you can say, this is the way it's going. This is the smallest one, and then as it is going on in this. And here, we arrange the elements of the set B in the descending order. Descending order means what? Here, these are here, these are largest, and then one by one it is going down. So here, at first we arrange the elements of the set A in the ascending order. Okay, these are ascending order. There is x1 less than x2, less than x3, less than x. This is the highest. Okay, this is the greatest two. So this arrow is showing that the magnitude is increasing. Here also, we are arranging this in the descending order. That is here, magnitude is, in this case, the highest is this one. Here also, magnitude is increasing in this direction. Once they are arranging one way each, after that, if I take here n elements, in how many ways? RC1 way, then each element here can be mapped in how many ways? In one way only. Suppose I select here 3 elements. Okay, such that here what we are saying, that at first what we have done, all the elements in the set A, in the set B. Set A in the ascending order. We arrange all the elements in the set A in what? In ascending order. Here we are arranging in ascending order. Ascending order. And here is elements of set B in descending order. Now, as the distinct element, so they can be arranged only in one order. So, element of x1, set A, x1 less than x2 less than x6. And in the set B, y1 greater than y2 greater than y3 greater than y2. Now, we select n elements out of R In how many ways? RC1, and then they can be mapped only in one. For example, here 1, 2, 3. Suppose we are in the descending order. That is A1 is the largest, and then A2, then A3, then A4, then A5 in magnitude. And here X1, X2, X3. That is here their magnitude is increasing. So as per the condition, what we have for decreasing? If the input is least, we should have maximum. So here for 1, we have only one option. So this is how we get the number of secretly decreasing function. Set A has 3 elements. 1, 2, 3. Set B has 5 elements. A, E, I, O, U. Now here NA, we have a 3 element. NB, we have 5 elements. So in this case, we can say, as we know, that as we denote that NA by N, NB by R, therefore, number of strictly decreasing functions equal to what? RCN 5C3.